Alrighty, so let's start the sulfuric acid industry. Now, for this process, we're going to be looking at what we call the contact process. There are other processes, but we're going to be looking at the contact process in chemistry unit 2. Right, for the production of sulfuric acid. It involves a series of chemical reactions to convert sulfur into sulfuric acid. The contact process is a key industrial process with broad applications, including in fertilizers, chemicals, and other manufacturing sectors. All right, so looking at stuff like this, the contact process, right? We're looking at three things: the burning of sulfur or sulfur containing compounds to produce sulfur dioxide. That is one. Two, conversion of sulfur dioxide to sulfur trioxide using a catalyst. And three, absorption of sulfur trioxide into water or sulfuric acid to produce sulfuric acid. Right? Water or sulfuric acid to produce sulfuric acid. Three things. You burn something, then you convert the dioxide to the trioxide, and then you inject the trioxide into water or sulfuric acid. All right, that's what we do. Step 1, producing sulfur dioxide. This process begins with burning the sulfur or sulfur-containing compounds such as iron pyrite. So pyrite is one of the sources there to produce sulfur dioxide. We see the reaction there will burn the sulfur. So what happens if we ask for the reaction of the combustion of sulfur? Or what happens when we combust pyrite? There's pyrite and there we're combusting it to produce the iron oxide and sulfur dioxide. Look at that. Iron oxide is impurity, right? So impurities like dust and arsenic, right, can be produced as well, all right, with the different impurities. So we're trying to do that, all right? So look at that, two reactions there. So the combustion of sulfur and the combustion of pyrite. And we know that combustion reactions are all exothermic. Why am I hinting to exothermic versus endothermic? We're going to see why. Because the answer is always Le Chatelier's principle. We're going to look at it in the future, right? So let's look at this now. The conversion of sulfur dioxide to sulfur trioxide. Now, first of all, the first part is creating sulfur dioxide. Not true. And what we're doing, we're burning it in the presence of oxygen, which is combustion. Not true. That is what we're doing. Step 1, we are burning something in the presence of oxygen. Step 2 now is more complex. We convert the sulfur dioxide that we got from step 1 to sulfur trioxide. Alright? To purify sulfur dioxide, right, or rather the purified sulfur dioxide is oxidized to sulfur trioxide in the presence of a catalyst. This step is a critical process now. It is using vanadium 5 oxide catalysts, right, which operates at special conditions, right? So now, for the conversion of sulfur dioxide to sulfur trioxide, what you need about 400 to 450 degrees Celsius, 1 to 2 atmospheres, vanadium 5 oxide catalyst. Alright? The optimal conditions are required to maximize the conversion while minimizing unwanted side reactions or decomposition of the sulfur trioxide. We don't want to decompose the gas, so we use these specific conditions. Now, we need to know the conditions. It is not an ask, it is not an if nor but. Alright? Let me be very real with you guys. You don't have to know it, You really and truly don't. Right? But the thing is, no, if you want, it depends on which grade you want, right? Or whether or not you want to understand the chemistry. Remember, I always say I tutor for you guys to understand it. I not tutor for exam. If that was the case, where they had to pass paper every single class, that is not the case. I want you to understand what the syllabus is trying to get to you. So you need to go through it. Grade 1's only, right? Right, Shani, grade 1's only. Last year when I saw a grade 2 and a grade 3, I was so ashamed. Remove them immediately from the group. Remove. Because what do you mean? Alright, so let's go. So the principles behind step 2 now. Now, not only do you need to know the reaction, but the syllabus says that the candidate must understand the chemical principles. So Le Chatelier's principle, right, with respect to temperature, pressure, and concentration, or in this case, it is, well, pressure or concentration of gases is the reason why we use these things, right? What is Le Chatelier's principle? Anyone here remind me of what Le Chatelier's principle is for me, please? What is Le Chatelier's principle? Me not continuing unless somebody tell me what Le Chatelier's principle is. So we'll stay here forever and ever more. You have to open your mic and tell me. Can't know that you guys know it. What is the Chatelier's principle? The reaction. Okay, so I'll accept the comment, right? So the reaction will favor whichever is least produced. Interesting. That is not the principle. I understand that what you wrote a while ago comes from the principle. So alright, you know, you have an idea what the principle is, or you know what the principle is. But what is the principle? Mm-hmm. Mm-hmm. Yes, I do understand exactly what you're saying. Alright. So fair enough, right? So a reaction in equilibrium will always move to counteract any changes made to that equilibrium. So if we're at equilibrium and we increase the temperature, we're going to be moving to counteract the change to regain equilibrium, right? So looking at stuff like that. So look at equilibrium constants in chemistry unit 1. Look at Kp, look at Kc, look at Ka, look at Kb, look at Ksp, we look at K stab, look at so many equilibrium constants. We must understand the principle by now, right? So looking at that now, the optimal conditions now, temperature, the reaction is carried out at 400 to 450 degrees Celsius. The temperature range strikes a balance between the optimal kinetics and the need to drive the reaction toward sulfur trioxide, right? A slight increase in pressure, about 1 to 2 atmospheres, helps to push the equilibrium towards sulfur trioxide, right? Since the reaction results to decrease in the gas volume. See it there? See, there decrease in the gas volume. Higher pressure favors product formation. The catalyst, right? The use of a catalyst, typical vanadium oxide, right? Vanadium 5 oxide, enhances the reaction's rate without being consumed in the process. That is the definition of a catalyst. Catalysts lower the activation energy, allowing the reaction to occur more readily at lower temperatures. That's why we don't have to increase the temperature so much. All right. Why we don't increase the temperature so much? Why is it that we don't increase the temperature past 450 degrees Celsius? Because wouldn't that increase the rate of reaction, so it should produce more sulfur trioxide, right? So why we don't do that? And don't tell me the decomposition of sulfur. We already have that out of the way. We don't want to decompose sulfur trioxide, rather. Right? So that's one. But according to Le Chatelier's principle, why don't we want to increase the temperature? Continue increasing the temperature to increase the rate of reaction. Why don't we increase it, right, to the point where decomposition of the trioxide will occur, right? So heat it to just about there. Why don't we do that? Any answers? I think we're seeing what's on the answer is on the screen. Not in the words, but the answer is at the reaction. This is the answer to my question. Why don't we increase the temperature past 450 degrees Celsius? What about the reaction can we know? Alright, to make it a bit simpler, what do we know about the reaction? Based on what you see on the screen, what do you know about the reaction?
One thing that I can tell you is
Anyone?
keep your expectations realistic.
From what is on the screen, it's exothermic. Exothermic, lovely, right? What does exothermic mean? Yeah, so it loses heat in the environment or it creates heat, right? Heat energy, right? No, Le Chatelier's principle did say something about temperature change. If the reaction is exothermic and we continue to increase the temperature, what will happen to the reaction? The equilibrium will shift, no so? If the reaction is if the forward reaction is exothermic and we continue to increase the temperature, the reaction equilibrium will shift to favor the reactants. But what we're seeking is the trioxide, right? So if we continue to increase the temperature, we're not going to create more trioxide. We're going to shift the equilibrium position towards the dioxide. So that is why we try to keep the temperature low enough now and try to use catalysts and stuff like that, because if we put it too high, the reaction equilibrium will favor the dioxide and not the trioxide. The first thing I said, I don't remember who was in my chemistry unit 1 class, but the first thing I said in chemistry unit 1 is that all we're doing is baking a cake. We take the information from the level of chemistry we did before, we take the information as ingredients, and all we're doing the level above is bake a cake. Alright? So all of this is chemistry unit 1. All we're doing now is using the concept that we have learned, and we put it together and use the knowledge properly. Alright? So lovely. We just need to understand why the things are like. The syllabus asks us, tells you, the candidate, to know the principle behind of the reaction here. You must know the principles relating to temperature, pressure, and why the use of a catalyst is there. Alright? Step 3, absorption of sulfur trioxide. Sulfur trioxide is absorbed into concentrated sulfuric acid to produce oleum. Alright? So it is also known as fuming sulfuric acid, which is then diluted with water to create sulfuric acid of a desired concentration. So the absorption of sulfur dioxide directly into water can result in highly exothermic in a highly exothermic reaction, generating a mist that complicates handling, so it is avoided. Right? So it is avoided. So we actually prefer to produce oleum, right, than to produce directly sulfuric acid because of the fumes that will occur, right? So we end up doing that. So we end up having this. So we absorb the sulfur trioxide into sulfuric acid to produce oleum, and then we dilute the oleum now to a preferred concentration of sulfuric acid. Oleum, H2S2O7, know the formula. Right? Especially if sulfuric acid industry comes, know the formula. Alright? So we have that there. Ready to move on now? I know I spent a lot of time on step 2. That is because the syllabus asks us to know the principles behind that. But now step 3 is simply adding our sulfur trioxide to our sulfuric acid that was there before, producing oleum, then diluting it. Alright? Ready now? Ready to move on? This is the contact process. This is the contact process. So the first thing we do, combustion chamber. Remember the first thing that we did? We burnt sulfur in the presence of oxygen. Right? Then now we convert the sulfur dioxide to sulfur trioxide using this process here, the conversion chamber. Remember the temperature is 450, the pressure is 1 to 2 atmospheres, and the catalyst is vanadium 5 oxide. And now there are two things that we do. We either take our sulfur trioxide and add it directly to water to produce sulfuric acid here. This is step 2 rather. This is step 3 really and truly, let's say 3A, step 3A. But we don't really prefer to do that. We prefer to do the absorption tower and add the sulfur trioxide directly to sulfuric acid to produce oleum. This is, let's say, 3B.
I'm jobless.
Really and truly, this is both step 3, but we prefer 3B. Then we dilute the oleum, which is step 4, into sulfuric acid. School is over. That is it. Simple, isn't it? Screenshot this page if you'd like. Screenshot it. Know it. Internalize it. Sleep with it. Eat it and breathe it. Alright? That is what we must do. Sleep it, eat it, and, because I must not. Because you have to. You have to know it. If you don't know this, you don't know the sulfuric acid in industry, and that is it. So this is what we call the contact process. All of this is the contact process. Alright? One thing to tell you now after is that in the conversion, when we increase the temperature to 450 degrees Celsius, right, because of the nature of the reaction, because the nature of the reaction is exothermic, right, there will be some sulfur dioxide that is still remaining. So what we'll do, we'll recycle the sulfur dioxide, right, and convert it again. So any sulfur dioxide still remaining, we'll push it back, right, and reconvert it. So 98% of the sulfur dioxide is actually created into sulfur trioxide, right? The remaining percent is recycled. Alright, so we're done. Moving on. This is another thing here. Hold on. Sulfuric acid concentration, vaporization, sulfuric acid vaporization. This is the reverse. Never mind. I'll take it out of the PowerPoint after. That's the reverse reaction. See what happens when you make PowerPoints on sleep, right? I was like, okay, since they know the contact process, let's reverse it. Yay. Okay, so I should remove this from the PowerPoint. But yeah. So sulfur compounds including sulfur dioxide and sulfuric acid play vital roles in various industries, including the food preservation and chemical manufacturing industries, right? So we need to discuss the importance of the compounds of sulfur. So sulfur dioxide in food preservation. First of all, sulfur dioxide is antimicrobial in nature, right? It inhibits microbial growth. So sulfur dioxide inhibits the growth of bacteria, yeasts, and mold, making it useful in preserving foods and preventing spoilage. So persons who do CSEC and CAPE food and nutrition, you don't know this like the back of your hand already, because this always comes up. Alright, we use it in preserving wine and beer as well. So sulfur dioxide is used in wine making and brewing to prevent microbial contamination during fermentation and storage. Alright, so it maintains wine stability as well to prevent unwanted fermentation. Alright, so when we finish fermenting to produce the beer, we don't want to ferment it all into alcohol. We want to keep remaining as a solution, right? So when we talk about proofing and overproofing, I should probably give you guys a talk about making rum, you know. Well, I don't want to support the idea of making rum at home. That is not advised. But we use sulfur dioxide to actually like stop the process, right? We kill off everything, so we stop the process of fermentation. Preservation of dried fruits and juices, so we use it prefers there. It also has antioxidant properties, right? That does not mean that you should eat it completely, right? But it's used to preserve, right, or preserve vitamins, right, and other sensitive compounds in foods, right? It prevents the oxidation of these things. This preserves the color and freshness of food. Alright? Now, I'll hint to sulfur dioxide, right, a little bit. Sometimes you buy your snacks, right? And you feel the snacks, and the snacks, they're halfway in the bag, and there's the bag of air. Nothing in the bag, no. Nothing in there. Right? Half of the entire snacks we buy is literally like sulfur dioxide and other preserving gases. So it's not that air is in the bag, you know, it's just that it's the gas is in there to preserve it. Right? So you're just using that to relate it back to that. It's used as a preservative. So when you buy a cheese tricks, and only half of it having chips, and the rest of it is just air, right? It's not air, it's preservative gases to make sure that it doesn't like rot in the bag, right? Right, so we have that there, and then you have sulfur dioxide sensitivity. Some individuals are sensitive or allergic to sulfur dioxide and sulfites. So food products containing sulfates must be properly labeled to warn consumers with sensitivities. So some persons are allergic to sulfur dioxide, so they can't just use a lot of sulfur dioxide in the products and not label it. So food labels are important. All right. Sulfuric acid. Now these words are tiny. All right, so sulfuric acid now, right? It's used in the preservation of foods as well, all right? Sulfur dioxide is commonly all right, fish all that. Sulfuric acid is used in the manufacture of phosphate fertilizers, right? Sulfuric acid is used to produce phosphoric acid, right? We don't learn that right now, right? But we use it in the phosphoric acid production, right, to produce phosphate fertilizers, and this application is crucial, right, for agriculture and food production, right. Also in chemical manufacturing, sulfuric acid is used. Listen, guys, question: for all the reactions across chemistry unit 2, no, like half of them use sulfuric acid as a acid media or a catalyst. Half of them, right? A lot of them. Acid hydrolysis of the ester, sulfuric acid, right? We're using not nitration, right? But in the formation of azo compounds, sulfuric acid. There's sulfuric acid everywhere. Sulfuric acid is used in the majority of our chemical reactions, right? That's why we're called to look at its production, right? So the production of various chemicals, including detergents, right? Saponification, right? Not only saponification specifically, right? Saponification produces soaps, right? But if you use acid hydrolysis now, you can create detergents, right? So that there dyes as well, production of our azo dyes, right? We know that we have to do it in an acid media for some of the reactions, right? We can create the dyes there and pigments. It's used in the production of pharmaceuticals as well. It is also used as a strong acid in many chemical reactions. The petrochemical industry also uses sulfuric acid as well for alkylation, right? To produce high octane components of gasoline, contributing to the efficiency of efficiency and engine performance, right? It's also used in electroplating and metal processing, right? So sulfuric acid is used in batteries. You guys remember the lead acid accumulator from CSEC, right? Or from module 2, chemistry unit 1, right? Lead acid accumulator is sulfuric acid in there, right? It's used to power automobiles and other machinery using these batteries, right? It's also used in water treatment and pH control. So sulfuric acid is used in water treatment to control the pH levels in industrial processes and sewage treatment plants. So sulfuric acid is a universal strong acid that we use for almost everything, right? It's used as a catalyst for many reactions. It's used to produce many different things that we normally use, right? And it's used in metal processing, electroplating, battery production, and water treatment. All right, and that is it for the sulfuric acid industry.